Hello, welcome back. So the previous video talks about the evolution of computers. It started from the purely mechanical computers such as the abacus and the slide rule, the machine of Blaise Pascal and Gottfried Leibniz, and it moves to the electromechanical, which is the punch card, as being invented by Ulrich, which is with the aid of business partners, it became the IBM, or the International Business Machine, as what we have come to know today. After that, the purely electrical computer machines, which is operated by vacuum tubes and relays. So the first generation of electrical computers is using vacuum tubes, which are so bulky that one computer could fit inside a room. Imagine how big that computer is. Now, on the second generation, transistors were invented by William Shockley, John Bardeen, and Walter Brattain when they are at Bell Laboratories. Now, the evolution of transistors paved way for the miniaturization of computers. Now, from a computer that fits inside a room, it is now significantly reduced to a desktop computer. When Chuck Kilby and Robert Nortonois developed a way of integrating circuits, that is, to integrate a lot of transistors into one single chip. Now, the fastest computing CPU today could contain millions, even billions of transistors connected together. And the current trend in computing is now the AI, or the artificial intelligence. It would be an advantage if we could at least know some of the data that the computers run as they operate. So for today, should be our learning objectives. Differentiate analog and digital signals. What is analog and what are digital signals? Then differentiate decimal and binary numbers. Lastly, we'll try to convert decimal numbers into binary numbers. That way, we'd be able to learn some of the data or signals sent through and out of computers. So what is analog and digital? There are two divisions in communications, that is analog and digital. Communications is the means of sending information and receiving information. So we have analog and digital. In analog or digital, signals are represented by voltage level. So in terms of analog signal, it is best described by this waveform. So the height of the signal is the amplitude, and the expansion or the compression of this signal is the frequency. And notice that at any particular time, the voltage values is different. So in an analog signal, we have an infinite number of voltage values. Same with when we talk, we have an audio waveform. This is an example of an audio waveform. So if we're going to play it, the amplitude, this is the amplitude, and this is the frequency or the pitch of the audio. How about in digital signals? In digital signals, there are only either two values, either high or low, logic 1 or 0, or if it is represented by a voltage, it could either be 5 volts or 0 volts, which means if 5 volts, that is logic high or logic 1, and if it is 0 volts, that is logic low or logic 0. The transition from high to low or low to high is abrupt, meaning it happens immediately. Unlike analog signals, it has to gradually increase or gradually decrease. In digital signals, it is abrupt. It could be best represented by the square wave. Now, since digital signals only have two values, either 1 or 0, it uses the binary number system. What is a binary number system? We're going to compare a binary number system and a decimal number system, which we have come to know. Binary means 2, or there are 2 possible digits, and decimal means 10 from the root word DC and bi. Bi means 2, DC means 10. So when we say bilingual, so 2 language, decimal means 10. There are 10 possible digits. Later on, after a few while, we'll understand what does this really mean. Let's move forward. So now let's understand the number system. In decimal, we have these place values: 10 to 0, 10 to 1, 10 to 2, 10 to 3, 10 to 4, 10 to 5, and so on and so forth. So that is what we have commonly known as the place values. We have the ones place, the tens place, hundreds place, thousands place, tens thousand, 100,000, and so on and so forth. So again, this 10 here is the base or the radix. It means that for every place values, there are only 10 possible digits. That is from 0 to 9. This is 0 to 9, 0 to 9, 0 to 9, and 0 to 9, and so on and so forth. So for example, we have these values here for each place value. So we can say then that the value is 53,942, or it means that there are 5 10,000s, 3 thousands, 9 hundreds, 4 tens, and 2 ones, or that is equivalent to 53,942. But in binary, since there are only two possible values, two possible digits, so the base or the radix is 2. It means that for every place values here, there are only 2 possible digits. And just like with the decimal, we have these place values. So for decimal, we have ones, tens, hundreds, thousands, 10,000, and so on and so forth. But for binary, we have ones, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. Now, does that ring any bell? Of course, those values are the ones that we commonly hear when we talk about the memories of our computer, such as the RAM. So I have a 4 gig RAM, an 8 gig RAM, and now suppose that we have values for each of the place here. So we have 1, 0, 1, 0, 1. Take note, we can only find either 0 or 1 in each place value, because there are only 2 possible digits in every place value, and that is either 0 or 1. So if we're going to convert that one in decimal, 101 is equivalent to 21 in decimal. Why is it 21 in decimal? Remember, if we go back to decimal, we have 53,942 because we add up everything that we multiply here, 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 and here, and then add them up, we have 53,942. That is why when we are at our elementary or even high school, we say that 50,000 plus 3,000 plus 900 plus 40 plus 2 is equal to 53,942. So in binary, we also do the same. We multiply the digit to its place value, and then we add them up. So we say there is 116 and 08, 14, 02, and 11. So therefore 16 plus 4 plus 1 is 21. To really make a statement on whether or not we have understood binary from decimal, let's do the basic counting. Now, counting is really very difficult, but since we learn counting and we are taught of counting, the moment that we know how to talk, we are being taught by our parents on counting from 0 to 1 to 10 up to 10, and from until what we have learned today. As I've said, counting is really very difficult, but we are so skilled in counting in the decimal number system that even in our daydream, even on our dream, we can count very well. So in decimal, we say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, 1 here is the next place value, and 0 is the least significant value, or the ones value. Now, have you asked yourself, why is it that 10 comes after 9, or 20 comes after 19, or 100 comes after 99? That is because, if you can remember, counting comes from the abacus counting system. So in every place value, remember, for decimal, we only have 10 possible digits, and that is from 0 to 1. So imagine these are the place values of your decimal number system, and there are 9 beads here. Now there are 10 beads here, but there are 9 beads here, and if the right side is empty, that means 0. So suppose that there are sheeps that you are going to count, a lot of sheeps, and it cannot be counted by your fingers, so you use the abacus. So when there are no sheep, though, of course there will be no beads here. So one sheep passes by, you move 1 bead, and then another sheep passes by, you move 2 beads. There are now 2 beads here, and now you know that there are 2 sheeps. But when you count it without using abacus, you say 1, then 2, right? Until all of the beads here are used up or moved to one side. That is also synonymous to having 9 here. Now after 9, do we still have another counting digit? None, right? So the moment we reach 9, we reset to 0, and then move the next place value into, increment the next place value by 1 bead. So that is how we do also in abacus. So we move 1, 2, 3, 4, 5, 6, 7, 8, 9 beads, or all the beads are moved to the right. Now there are no more beads to move, so what we'll do is to reset all those beads, move it back to the left, and then increment one of the beads to the right. So we now have 1 bead here for the 10th place, and then 0 beads for the 1's place. That is 1, 0. So that is when we count again. If we continue this 10, we have 1, 1, because this would not be added. So 1, 1, 1 2, 1 3, 1 4, 1 5, 1 6 until all of the beads here are used up. So we have 19. So after 19, we don't have any more counting beads here or counting digits here. So we reset to 0, and every time we reset to 0, we increment the next place value. So we move another bead here. So we now have 2 beads here. 2 and 0, it becomes 20. So until all of the beads here are used up, so we have 9 and 9. So from 99, there are no more counting bits or digits that can be used. So we reset to 0, increment the next place value. So since this is 9, no more counting digits can be used. So reset to 0 and increment to the next place value, which is now 1 or 100. That is why 100 comes after 99. I hope you understand that one well. So that is how difficult counting is, and I will tell you that counting is really difficult. It's just that we are so used to counting in decimal. But what if we count in another number system? Let's say binary. Now in binary, let's try to count and understand why is it that this is different from decimal, and why is it that counting is difficult. So let's begin. That's 0, 1, 1 0, 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1, 1 0 0 0, 1 0 0 1, 1 0 1 0, 1 0 1 1, 1 1 0 1, 1 1 1 0, and 1 1 1. So is it easy or difficult? Probably difficult, right? Now we are just using 1 2 3 4 place values counting. In fact, this is a binary number that is equivalent to 15. So it's just like counting from 0 to 15 in decimal. So from 0 to 1111, that is 15. Why is it that it is 15? Because this place value, it belongs to the 1s, then the 2, the 4, and the 8. So if we're going to add everything here, we have 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So when we start at 0, we have 0 0 0 0, so the value is 0. So when the value here, the binary value is 0 0 0 1, the equivalent is 1. So for 2, we have 0 0 1 0. That is for 2. How about for 3? So we have 2 plus 1, that will be 1 1. So 0 0 1 1. How about for 4? So we have 4 here, so this would be 1, and the rest would be 0. So 0 1 0 0. How about 5? That would be 0 1 0 1. And how about 6? That will be 0 1 1 0. And for 7, 0 1 1 1, because when we add up to 4 plus 2 plus 1 is 7. For 8, we have 1, then the rest would be 0 0 0 0. And for 9, 1 0 0 1. For 10, 1 0 1 0. And then for 11, 1 0 1 1. And for 12, 1 1 1 0 0. For 13, 1 1 0 1. 14 1 1 1 0, and 15 is 1 1 1 1. Let's go back and try to follow counting. 0 1 1 0 1 1, 1 0 0 1 0 1, 1 1 0 1 1 1, 1 0 0 0 1 0 0 1, 1 0 1 0 1 0 1 1, 1 1 0 is 1, 1 1 1 0 1 1 1 1. It is really difficult in counting binary numbers, but anyway, we are not here to count binary numbers, but we'll understand how binary and decimal are related, or how we convert binary to decimal or decimal to binary. So how do we convert binary to decimal? So the procedure is really that simple. There are only 2 steps. Get the product in each place value by multiplying the digit in the place value. Get the sum of the product of each place values. Really, the statement here doesn't make sense, but it would make sense if we'll have an example. So for example, if we're going to convert 1010110 base 2, because that is in decimal, in binary, converted to decimal. So the first thing we're going to do from the first procedure here, get the product in each place value by multiplying the digit with the place value. So we're going to arrange our digits here to each place value. So we have 1010110, that is 1010110. It means that this belongs to the ones place 2, 4, 6, 8, 16, 1, 2, 4, 8, 16, 32, and 64. So get the product, so we multiply the bits here, the digits here, to its place value, and then get the sum of the product. So take the sum of the products. So we first multiply. This would be 0, this would be 0, this would be 4, 2, and 0. So we're going to add everything here. That will give us 86, because 64 plus 16 is 80, plus 4 plus 2 is 86. That is the sum of the products. Now it's your turn. Now try this. Convert the following from binary to decimal. Now get your paper and pencils ready, and then try to solve for this one on your own. Try not to cheat, because this is for your own good. Pause the video, and then afterwards I'll show you the answer, and check whether you have correctly answered everything 1 to 5. The answers are 5, 6, 8, 109, and 77. I hope you got everything right. Okay, how about the other way around? How do we convert decimal to binary? Now these are the procedure. So first is divide the number successively by 2 until the quotient is 0. Remember, take note of this. Successively by 2 until the quotient is 0. Then take note of the remainders. The remainder is either 1 or 0, and it would form the binary number. So whatever the number is, if we're going to divide it by 2, it could only either have a 0 remainder or a 1 remainder. For example, we divide 7 by 2, that would be 3 remainder 1, right? If we divide 10 by 2, that would be 5 remainder 0. So those are examples. Then read the remainders from bottom to top and write the binary number from left to right. And again, this won't make sense until we have an example. So first example, convert 98 to binary. So first is we're going to divide 98 successively until the quotient is 0. 98 divided by 2 would be 49 remainder 0. So 49 remainder 0. Because if we are going to multiply 49 times 2, that would give us 98 plus 0 is 98. Next, 49 divided by 2. That will give us 24 remainder 1. Why? Because if we multiply 24 times 24, that will be 48 plus 1 is 49. So remainder 1. Next, 24 divided by 2. That would be 12 remainder 0. Right? Then 12 divided by 6 is 12 divided by 2 is 6 remainder 0. 6 divided by 2 is 3 remainder 0. Then 3 divided by 2 is 1 remainder 1, and 1 divided by 2 is 0 remainder 1. Now read the digits from bottom to top, and then write it from left to right. 1 0 1 1 0 0 0 1 0. So this is the value of our binary equivalent to 98. Now try this. Now if everything is not clear yet, so you can always go back to the video and then replay it. But this time I want you to solve for the conversion of decimal to binary by this 1 to 5. Again, pause the video, get your paper and pen, solve it religiously without any help from your calculators, and then I'll show the answer right now. So the answers are 10110 for number 1, 10110 for 2, for 3, 4, and 5. Did you got everything right? If not, try to review your solution. Now, I believe we now can understand what this meme really means. There are 10 types of people in the world, those that understand binary and those that don't. Where are the 8 here? Because they're on there. It says for a while ago that there are 10, but actually the 10 here represents binary. So there are 2 types of people in the world. 10 is in binary is 2. This is under 1's place and this is under 2 place. So there are 2 types of people in the world, those that understand binary and those that don't. Go ahead and spread the meme. Now there are other number systems aside from decimal number system and binary number system. We have the octal number system. Octal, from the term here, octal means 8. So there are 8 possible digits in every place value. So the base or the radix of an octal number system would be 8. And each of the place value here would only have either 0 to 7 values. Then we also have hexadecimal number system. Hexa means 6 and deci means 10. So there are 16 possible digits. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then A, B, C, D, E, F. So when we count in hexadecimal, we say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then A, then B, then C, then E, then F. That is why the place values for each of the base or radix of place values of hexadecimal number system is 16, because there are 16 possible digits that could be used in each place values. We have 0 to 9 and A, B, C, D, E, F. That is why maybe you might have asked, if you try to look at your scientific calculator, you'll find letters A, B, C, D, E, F, and you might wonder where are the rest of the alphabet, G, H, I, J, K, L, M, N, O, P, because that is if you're going to use the hexadecimal capability of your calculator. Actually, you can convert binary to decimal, decimal to binary, binary to octal, decimal to octal, decimal to hexadecimal using your calculators. Or when you use your computers, your calculators from your computers, there are programming options there that can convert binary to decimal. So when we solve for an exercise using let's say converting binary to decimal or decimal to binary, we're going to use we can not use the calculators, but to verify our answers. But it would be best if you try to solve it for yourself manually and then verify it using your calculators. Binary numbers alone are going to convey an information, because there are only 2 different values, either 0 or 1. So how would you be able to convey information if the signals running on your PC is just zeros and 1? So you might ask yourself, how on earth would a computer able to process such a complex task using binary numbers alone? Now, one good example is that if you have a flashlight and you're going to flash lights to send signal, you can do that, right? But what if I'll tell you, if, or would you believe in me if I say we can convey information or even read books using even the flashing of light, the turning on and off of lights? That's what Morse code is all about. So in radio telegraphy before, Morse code is being used using dots and dashes. In fact, if you Google, or no, if you try to look at YouTube, the way Morse code is being used, you can hear the machine goes because those are binary codes. So dot and dashes. So dot means dot and dash is dot. So just like an on and off of a flashlight, or now what we know as the binary number or binary signal, or 0 or 1, high or low, logic 0 or logic 1, or in terms of voltage that would be 5 volts or 0 volts, right? So we can of course convey information, but what Morse code did is not just to send dot and dashes, but a group of dots and dashes. So that is how information is conveyed in digital communication. So a group, they are grouped together. Now, one binary code that is being used is the BCD, or the binary coded decimal. Binary coded decimal have 4 bits, or if you're going to press the value in press a button in a calculator, it will give us it would be converted into a 4-bit information. So for 0, it would give 0000. So not just 0. If you in press 1, it would give 0001. 2 is 0010. 3 is 0011, and so on and so forth. So it gives, or it sends signal to the calculating chip here into this format. So there are now 4 bits, or what we call as nibbles. So 4 bits are called nibbles, and 8 bits is called byte. So you might have come across the term byte, or BYTE. BYTE means an 8-bit code. So for nibble, we have 4 bits. So for example, number 9 is represented by a 4-bit signal, which is 1001, because there are 1, 2, 3, 4 bits. And same goes for number 7, it's represented by 0, 1, 1, 1. So when we press our calculators, it sends 1001 to your chip. And if we press 7, it sends 0111 to your chip. That's a 4-bit or 4 nibble, or 4-bit, or what we call as the nibble. Now again, if there are 8-bit, that is called a byte, or BYTE. That is why we often heard the term kilobyte, megabyte, gigabyte. Now a 4-bit code is limited only up to 15 possible values, right? There are only 15 possible combinations. So we have this is 9, right? So now if we continue the combination, number 10 would be 1 0 1 0 11, and then when everything is 1, that would be 15. So there are only 15 possible combinations. Now that's limited to 15 possible combinations only. But if we use 4-bit, or the code is only limited up to 15. But in alphanumeric, like the alphabet and the number itself, 0 to 9, that is, it needs 64 characters, 64 combinations. So 4-bit is not enough. So that is why an 8-bit code is needed. So for 8-bit, there are 1, 2, 4, 8, 16, 32, 64, 1, 2, 8, 255 possible combinations. That is why our keyboards are specified into 255 characters, because it could the 8-bit could accumulate up to 255 possible combinations, because there are 1, 2, 3, 4, 5, 6, 7, 8 bits of information. So now it gives rises to the alphanumeric codes, an 8-bit alphanumeric codes. The first one is the extended BCD interchange code. BCD is the binary coded decimal, so it is extended, so from 4-bit it becomes 8-bit or a byte. Then next is the most popular is the ASCII, or the American Standard Code for Information Interchange. This is the code right now being used up to now by our keyboard. So when we press any buttons on our keyboard, it sends signal to our computer, to our CPU, in an 8-bit format. So for example, if we press letter A, capital A, it could maybe send an 8-bit combination such as 10101111. That is 8-bit. Or for letter B, maybe 11011010. So there are codes in that one. In fact, when we Google on the ASCII code, it will give you the binary equivalent on each of the characters, like such as A, B, C, D, or the alphanumeric, or the special keys such as asterisk, comma, ampersand, dollar, and everything that we'll find on your keyboard. Now, of course, this would be important, but this would we would consider binary arithmetic on our on our next lesson. Now, consider this. Encoding and decoding means to cipher and decipher. In communications, we do ciphering, meaning we convert a message into a unreadable message, and of course, the one decoding it should know what is the, or how to decode, how the message is being ciphered. So when we encode and decode, that would be very important in communication. So if we use flashlight, we can create our own code. We can send alphanumeric data or information using the turning on and turning off of a flashlight, because but of course the receiver should know also the code. What code are you using? So if we use Morse code or the ASCII code, that would be possible. So important thing is we know how to cipher and decipher when we want to convey information. So the receiving end and the transmitting end should have common language, or what we call as the protocol in computer communication. So the protocol, or the common language. So if you send Chinese information to a Japanese receiver, they would of course not understand each other. So the language should be the same. That is true also to computer communication. Now, I want you to think of ways in ciphering and deciphering. Maybe you can create your own, or borrow a ciphering and deciphering methods in communications from different sources such as Morse code. Then try to post a secret comment in our forum and challenge everybody to decipher them. But of course, you need to reveal the real message and the means of ciphering it. So when we send, for example, I love you, you send it in a code and let everybody decipher it or decode it if nobody else can. So decipher it yourself, and then tell us how did you cipher it and decipher it. Okay, have fun. That's it for today. Thank you, and have a nice day.